this charity called Reach Out, and I was wondering, we do a lot of wildlife conservation as well as humanitarian, and I was wondering if you could start a quick 30-second announcement.
Yeah, that's a good idea.
Yeah? Thank you.
Good. So just a reminder that the first assignment is out. So if you should try to finish the prologue exercises if you haven't already done so, and start working on the assignment. And I just also remind you about the lab sessions. This lab sessions will be continuing in weeks 4 and 5. If you need some assistance with the lab exercises or the assignment, you can go along to those lab sessions. So the times are in the lecture slides from the first lecture. I'll try to also put it out as an announcement, as a reminder. Oh, excuse me. Okay, so today we're going to start talking about path search, which is chapter 3 of the textbook. Now, just to see where this fits in, so if you remember, we talked about reactive and model-based agents that choose their actions based only on what they currently perceive or what they've perceived in the past and stored in their memory. But then a planning agent can use search techniques to plan several steps ahead in order to achieve its goals. And these search strategies fall into two categories, which in the textbook are referred to as uninformed search strategies and informed search strategies. The informed ones, sometimes we also call them heuristic search strategies. So the informed search strategies make use of an estimate of how close you are to the goal, whereas the uninformed ones, you don't know how far you are from the goal. You have no idea how close you are to the goal. Okay, so we start with the uninformed one and then move on to the informed. Now, we're going to rely to a fair extent on this example from the textbook. So this is based on the map of Romania. So you imagine that you're on holiday in Romania. You have to get to Bucharest within the next couple of days to get your flight home. You happen to be in Arad, and you're given this map, and then you've got to plan a path to get from Arad to Bucharest. So it's quite a simple example, but an illustrative one. This is obviously very low dimensional, it's only 2-dimensional, but then we'll move on to other problems such as the 8 puzzle and Rubik's Cube. So Rubik's Cube is an example of, which it's a similar kind of path search algorithm, but the branching factor and the dimensionality is much bigger. So you imagine that you're on holiday in Romania, you're in Arad, the flight leaves tomorrow. So you have to formulate a goal. So remember the piece description, the performance measure is getting to Bucharest on time. And then we have to specify the environment or the task. So we're going to divide it, we're going to see this as a kind of state space search, so we need to see this as discrete states and discrete actions. And so the states are going to be the cities on the map, and the operators or an action is to drive from one city to another. And a solution is a sequence of cities. So if I tell you the cities you've got to visit in order, then it's assumed you can look at the map and follow the directions to get from each city to the next. Okay, so there's a goal test to check whether we've achieved the goal. So in this case, there's one goal state, which is at Bucharest. For some of these problems later, there may be multiple goal states. And then we have to decide on, so this again gets back into the performance measure, we have to decide what whether we achieve the goal, but also how good the path is. So do we want to pick the path that's got the shortest number of steps, that's got the sum of the distances is smallest, or the whatever? And our answer may vary depending on which evaluation metric we're using. Okay? Now, there's always a fair bit of abstraction going on here. So when we say Arad to Zerind, that's actually driving from Arad to Zerind is a complicated task in itself. That's what all those self-driving people at Google and Uber are working on. So you have to control the vehicle, you have to look at the road signs and all that, but we're just abstracting that away for these purposes. We're not concentrating on that, we're concentrating on just the path itself. But it'll work fine as long as we make the assumption that the driver, well, the other question is when you say that you're in Arad, where in Arad actually are you? But we make the assumption that if you begin anywhere in Arad, you can get to a specified point in Zerind, or some point that's in Zerind. And if you can do that for every pair of cities, then you'll be able to execute the path successfully. So we make a distinction between kind of toy problems where the description is concise and exact, and then real-world problems where you don't have an agreed description, and so coming up with a description is part of the process. So I don't have a prop for this, but these are kind of these sliding tile puzzles where this is the goal state, this might be an initial state, and the idea is you slide these tiles one at a time. At each time step you can slide one tile into there's always one empty spot. So I could slide, for example, the 5 over here, and then I could slide the 8 up, and then the 3 over, and by doing a sequence of those moves, you hope to eventually get the thing into this goal state. So if we look at how to formulate this, well, integer locations of tiles. So again, we talked about discrete versus continuous domains. So we assume that this is a discrete domain. We don't consider the possibility of a tile being halfway between one position and another. Of course, in reality, it can get jammed, and then you've got to kind of push it and stuff, but we don't worry about that. The operators. Now, you could specify which tile to move, but in some ways it's better to think about it this way, that the blank, the only tiles that if we think about the tile, well, certain tiles aren't allowed to move. So we couldn't move the 1 here, or the 4, or the 7, or the 8. The only tiles that can actually move are the ones that are next to the blank. So this tells us the branching factor, effectively. This tells us how many actions are possible in each state. At most 4. In each state, we have a choice of at most 4 possible actions. Sometimes it's less. If we started in this state, we'd only have a choice of 2 possible actions. The goal state, there's a unique goal state that's given, and the path cost. Now, this is important too. Normally, we regard one tile moving as one move, but there are some people. Well, for example, let's imagine we started in this state and we moved the 8 across, and then if we moved the 8 to here and the 7 to here, we normally regard that as 2 separate moves. But some people would say, well, you can stick your fingernail in there and move the 7 and the 8, slide them together, and just slide the 2 of them across. Maybe I just want to count that as one move. It's like I could move 2 tiles in one move, or the same thing with the 3 and the 6. So if you if you count the moves in that way, and then I ask you what's the shortest solution, then you may actually come up with a different answer. So you have to be very clear about how you're measuring the path cost. This is just another example that was provided with the textbook, a little bit fanciful in a way, but let's suppose you want to get a robot to assemble a certain kind of object. This is based on work that was done by Donald Mickey in the 1970s in Edinburgh, I think. And so let's suppose it has to figure out for itself how to build the object. It's not pre-programmed. Well, here the states would perhaps be real valued coordinates of robot joint angles and parts of the object to be assembled. And the operators might be continuous motions of the robot joints. And the goal would be assembly of the object. And the path cost might be the time to execute. So continuous domains can also be brought into the same framework, and we will be discussing about robot navigation. If a robot is moving around, you may want to minimize the time rather than the length of the path. If it follows a curved path, it has to move more slowly, so it may be preferable to find a path whose distance is a bit longer but is straighter so that it can be traversed quicker. So it's quite a general framework. But at the moment we're just looking at the discrete case. Now, Rubik's Cube, again we've got the same considerations. This is really very similar to the 8 puzzle, the sliding tile puzzle, but in 3 dimensions. So the states would be just configurations of the cube, and again we don't consider intermediate states like the one shown in the picture. We just only consider sliding from this state to that state. The goal test, again, there's a unique in the case of this 3x3x3 cube, there's a unique solution. Actually, I'm not entirely sure. With the 4x4x4, I'm not sure. There might be multiple solutions where little cubies have been swapped or something. But here there's a unique solution. Now, the operators and the path cost, again, you can have this issue about how you measure the cost. So, well, let me ask you, how many choices of action do you have when you're solving Rubik's Cube? How many possible actions are there at any given time? Sorry? Hard to count. No, for one, if I just want to make one move, how many ways are there to make one move? 6. Okay, so, right, well, that's a possible answer. So, who said 6? Yeah, so 6 is the number of faces. So what did you say? How many? 24. 54. Anyone else want to make a guess? Well, the person who said 6, yeah, 6 could be the correct answer in the following situation. I say, okay, there's 6 faces and I can pick which one to turn. Let's say for some reason I insist that I always turn the face clockwise, never anti-clockwise. Then I would only have 6 choices. And I could solve the cube using only those actions, because if I wanted to turn the thing anti-clockwise, I could just turn it 3 times this way. Right? So that is a valid answer. Okay, 6. Now, I think 54 is a little bit high, but could someone think of an alternative answer other than 6? 12, yeah. I think 12 would be the normal way of looking at this, because you say, well, you know, I don't want to discriminate against people who are left-handed. If what you really want to do is turn the thing to the left, you should be able to just do it directly in one move instead of wasting 3 moves. So that makes sense. So 6 is possible, 12 is possible. Is there another reasonable answer to that question? 15. How did you get 15? You're joking. You're close though. 18. Good. Who said 18? Yeah, so tell me why it would be 18. That's right. So this is related to what we talked about with the sliding tile puzzle. Let's suppose I want to turn this 180 degrees. Well, you could regard that as 2 separate moves, but on the other hand, you know, if I get a bit of practice, I can just do it in one motion. So why should I be penalized? That should just be counted as one move, right? If you're building a robot that's trying to solve the thing in the fastest time, it can probably do a half turn in almost the same time as doing a quarter turn, right? So we've got 3 different, you know, ways of formulating this, and yeah, like if I give you an initial condition, you can see how the answer may depend on what I choose. If I give you this initial condition, depending on those 3 formulations, you may come up with a different idea of what is the fastest, or what is the shortest cost solution to that from that position. Good. Okay, now how do we program this? Well, we do basically a tree search. So let's look at the graphics first. So we're in, if we think about our map of Romania, we start out in Arad, and then from Arad we can go, the 3 places we can drive to from Arad are in Sibiu and Timisoara, and then from Sibiu we can drive to these 4 places, and from Făgăraș we can drive to these places. So this essentially becomes a tree. The set of all possible paths, in fact, forms a kind of natural tree structure. And what we're trying to do is find the path somewhere in that tree. So this is actually a solution here. Bucharest is the place we were trying to get to. And so that's where this path lies in the tree. Now, so you know, but this is the process that we actually go through, is like expanding nodes. So we have a rod, and then we say that we expand a rod. Expand a rod means we kind of cross that node out and add 3 more nodes to the tree. And then we decide, okay, now I'm going to expand Sibiu, so I kind of cross that out and add 4 more nodes. And then I expand Făgăraș. And when I say cross out, of course you don't literally remove it from memory, but you just keep in mind that that node has already been expanded, so it's not available to be expanded again. Okay? So it's a process of always deciding which node to expand next. And the other thing is that the nodes, so at any given time we have a tree, we have some nodes in the tree that have already been expanded, and then we have nodes, we have potentially nodes that haven't been generated yet. Okay, so these nodes, like, theoretically exist, but I haven't found them yet. So my tree is actually sort of expanding. So there's nodes, potential nodes that haven't yet been generated. There's nodes here that have been generated but not expanded, and then there's nodes that have already been expanded. So the set of nodes that have been generated but not yet expanded form what's called a priority queue. And basically all of the search algorithms we're going to discuss work in the same, they have the same basic structure, but the only way they differ is the choice that they make of which node to expand next. Okay, so this is the form of this algorithm. So we start with a priority queue. Now, at the beginning, the priority queue consists of just one node, which is the initial state. And then from among the nodes that are available for expansion, we choose which one to expand. We check whether that node is the goal state. If it is, then we can stop. Otherwise, we expand the node by applying all possible actions to generate all its children. And it can happen that the queue becomes empty. So sometimes no path exists from the start state to the goal state, in which case eventually we expand every possible node and then we don't have anything left to expand. At that point we would stop and say, okay, there's no solution. Otherwise, we keep looping around until eventually we find a goal state. Okay, so this is the structure of all these search algorithms. Now, notice that this tree is well, there's a difference between the states and the nodes in the tree. So it's possible that the same state may occur twice. So a RAD occurred here and it also occurs here. Right? So there isn't a one-to-one mapping between the states and the nodes. And usually with the nodes we store a bit of extra information. So depending on if you were going to program, we're going to mainly be looking at Prolog, but if you were going to implement this in Java or Python or some other language, this is the sort of information you would normally keep with each node. You would try to remember what its parent node is and what operator was applied to get from that parent node to this node, and so on. So this could be implemented using these abstract data types. You have to make a queue. You have to have a way of checking whether the queue is empty. And then you have ways of inserting items into that queue and removing them. Okay. Now, the search strategies that we're going to look at, we want to be able to have a way of comparing them with each other. And we're going to compare them in along four different measures. So completeness, optimality, and time and space complexity. Okay, so completeness says, is this guaranteed to find a solution assuming one exists? Optimality is saying, does it always find the least cost solution based on our definition of cost? And then how many nodes, so the time complexity we measure in terms of how many nodes are generated or how many are expanded. And the space complexity is how many nodes have to be stored in memory at the same time. And in terms of the time and space complexity, they're measured in terms of these things here. So there's the maximum branching factor, the depth of the least cost solution is called D, and then the maximum depth of the search space is M, which in some cases may be infinite. So let's, just to recap, B is so what's the branching factor for those sliding tile puzzles? Does anyone remember? 4, that's right, because 4 is the maximum number of moves available. And for this Rubik's Cube, as we were discussing, the branching factor could be 6, 12, or 18, depending on how we define the problem. Now, several of you have already taken an algorithms course where I'm not going to we're going to take a fairly informal approach to it here. but just briefly, if I've got two algorithms and I want to know which one is faster, one way to do it would be benchmarking. You implement both algorithms and you run them on the same computer on different inputs and sort of measure the speed. But a more principled approach is that you do some mathematical analysis of the algorithm. Now, the benchmarking is a legitimate exercise, but there's all sorts of issues involved with it. You have to implement the two algorithms using the same. You have to run them on the same hardware. Implement them in the same programming language. Try to keep them as much as possible, as similar as possible, the way they're implemented, and run them on a bunch of different inputs and do statistical analysis and all these kind of issues. What we're going to focus on more is the analysis of the algorithms. Now, this is the formal definition as this big O. We say that you measure the size of the input n, the size n of the input, and then T of n is the running time of the algorithm for that input in terms of the number of nodes expanded and so on. And technically, we say that Tn is order of some function f of n if there's some number n0 such that for n larger than n0, Tn is less than equal to some constant times f of n. Now, for our purposes, we're mainly going to be dealing, most of the algorithms we're looking at will be sort of exponential or quadratic or perhaps log linear. So I think this will become a bit more apparent as we go along. Okay, so we're going to start with the uninformed search strategies and then move on to the informed ones. So the uninformed strategies we're going to look at are these: breadth first search, uniform cost search, depth first search, depth limited search, and iterative deepening search. And yeah. We might look at bidirectional search as well, which is sometimes considered as uninformed. And then afterwards, we're going to look at informed search strategies. So as I said, these uninformed strategies, what we're assuming is that you have no idea how close you are to the goal until you actually reach it. So you don't know whether you're one step away from the goal or a million steps away. And we just have to do the best search we can under those circumstances. Okay, so the simplest of these is called breadth first search. Now, what breadth first search does is it, and again, this is, I encourage you to have a look at these videos on the Open Learning, that I've put on the Open Learning website, because they explain these things in more detail, but I'll just kind of draw your attention to the most salient points here. So you start by saying, okay, I'm in a RAD, and then I look, okay, what are all the places I can get to, what are all the places I can get to in one step from a RAD, which is those three cities. And then I say, okay, well, what are the places I can get to in 2 steps from a RAD? And that's these ones, right? So you kind of expand out, you search very systematically, all the things that are 1 step away, all the things that are 2 steps away. And it's visually, I think, nice to look at this picture, because there's this sort of inner circle and the outer circle. So the inner circle is the nodes that have already been expanded. The outer dotted circle is the nodes that have been generated but not yet expanded. And then the other nodes outside that haven't been generated yet. And the thing finishes when you get to this point here. Eventually, Bucharest is actually, the shortest path to Bucharest is 3 steps from Arad. So if we were to expand Fagaras, we would see Bucharest. Okay. So this is just the same idea, but without the map. And we still have some ambiguity about the order in which to expand the nodes. So I have to expand everything at depth 1 before I move on to anything at depth 2, but the algorithm doesn't really specify which of these to expand. So by randomness, I've chosen to expand Zarin first and then these others. All right, so let's analyze this. So is it complete? Yes, it's complete if B is finite. If the branching factor is finite and the shallowest goal is at some depth D, then because it's so systematic, you expand nodes at depth 1 and then 2 and then 3. And so if the first goal is if the first goal is at depth D, then when you get to depth D, you're definitely going to find the goal. Now, and is it optimal? Yes, it is optimal, because if the shortest path to the goal is leg 3, it'll find that and then it'll stop. It's not going to look for any path of length 4 or longer. So if there is another path to the goal that's longer, it won't find it. So it'll always find the shortest one if what we're interested in is the number of steps. Now, what about the time and space complexity? Well, the time complexity, if you think about this, so the branching factor, there's one node at depth. What's the maximum number of nodes there could be at each depth? Well, there's one node at depth 0. There's at most B nodes. If every node had, and that's the other thing with this theoretical analysis, we're often looking at the worst case rather than the average case. So the worst case is where every node has the maximum number of children it possibly could have. So you could have B, if the branching factor is B, you could have B nodes at depth 1, and then each of those B nodes could have B children. So the number of nodes at depth 2 could be B squared, and at depth 3 could be B cubed, and at depth 4 could be B to the 4th. So the number of nodes could grow exponentially. So the maximum number of nodes in the whole tree before you find the solution could be this. And this is an arithmetic progression. This is a geometric progression, which is equal to this, and this is roughly equal to b to the power d. So this is the time complexity is order b to the d, and the space complex. Right. Well, then the space complexity is also order b to the d. So this is the thing. Remember, in this case, so in this case, the solution is at depth 3, so it's going to be at the next row, but it is possible that it might, in the worst case, the solution may come off the last node in the line. I might have to expand all of these before I get to that node. And so I would expand everything in the next row, and the very last thing would be the solution. And I have to keep all of those nodes in memory because I don't know yet whether I'm going to have to do another expansion. So you have to store everything at that depth in memory. So you need enough space to store b to the d nodes in order to implement this algorithm. Any questions about this? Okay, now, this is optimal if optimality means minimizing the total number of steps. But now, let's suppose I tell you that actually some of these roads are longer than others. It's a bit, I'll just expand that a little bit. So now I'm going to give you a bit of extra information on this map. I'm going to tell you the length of each of those roads. And if you think about it, well, really, I'd rather minimize the distance rather than the number of roads. Yeah, so what's really important is taking a path which has the least distance. Now, the breadth first search is always going to find this path because it's got 3 steps. But if you actually add up these numbers, there's this other path here which takes 4 steps, but the distance is actually shorter than this one. It's a little bit subtle. The distance, let's say from Sibiu, the distance here is 310, but the distance here is 198 plus 80, which is 278. Yeah, this distance here is slightly less than that distance. So really what we want is an algorithm that will find us the shortest distance path rather than the shortest number of steps. And so if we define the cost in terms of that, in that way, then we need a different algorithm to find the shortest path, which is called uniform cost search. Okay. So we expand the root node first. Right, so this, in uniform cost search, when we're choosing which node to expand, we always expand the node whose total path length from the initial node is the minimum. So again, let me go to just still, I think it's easier to understand looking at stills from the video. So here, right, so we start by expanding a rad. Now with breadth first search, we had an equal choice of these 3 cities, but with uniform cost search, we actually look at these distances. So this is 140, that's 75, 110. We expand Zarind first because it's the shortest path. Oops. Right, and then now we've got a choice of 3 cities now, and remember the total path, what's important is the total path length. So this Aradia, the path length from here to here is 146, which is bigger than this, and actually the shortest one is Timisoara. So we expand Timisoara, and we keep going in this way, and we always expand the one whose total path length is shortest. So when we reach this point here, we have, if you add this up, Fagaras is 239, Vimniku Vilsia is 220, and this is 229, so the shortest among these is Vimniku Vilsia. Now, then the shortest among these is Fagaras. Now, this is important. So once we've expanded Fagaras, we've generated, the goal state is Bucharest. So at this point, the goal state has been generated, but it hasn't yet been expanded. And so we can't stop. So we have found a path to Bucharest, but we don't know yet whether it's actually the shortest one. So we can't stop the algorithm there. we have to keep expanding as long as there's other choice. If there's any city whose distance is less than 450, there's still a possibility there may be a shorter path through that city. So the shortest one here is Mahadia. Oops. So we expand Mahadia, and then we expand Pitești, and notice what happened here. Before we expanded Pitești, Bucharest was 450. Afterwards, it goes down to 418. So sometimes our estimates of the distance change as we expand more nodes, and we still can't stop yet because these ones are shorter, so we have to expand Dobreta and Craiova, and it's only at this point that we can stop the algorithm because we've already expanded every path. We've expanded every node that's closer than 418 miles, and so we know that no shorter path exists. Okay, so this is sort of the same idea without the graphics. Okay, so what can we say about uniform cost search? Well, you can prove these things. So we won't go through the formal proofs, but you can kind of imagine how this works. So in order to prove that it has these properties, we have to make the assumption that every path has a certain, there's some absolute minimum epsilon, and every path has a cost of at least epsilon. Because if you allow roads that are just shorter and shorter and shorter going to zero, then it becomes a kind of problem of Achilles and the tortoise. That you may, like let's suppose you have a road that's 1 kilometre, you have a road that's 1 mile, and then a road that's half a mile, and then a quarter of a mile, and then an eighth of a mile, and then a 16th of a mile, and every road is 1/2 the length of the previous road, then even though the goal is only 2 miles away, you'd have to go through an infinite number of cities to get there. So we want to avoid that issue. So there's some number epsilon, and every road is at least length epsilon. Then we can actually prove that these properties. It's complete. Well, the complexity, I mean, the idea here is, let's suppose that the actual shortest path is C star. Every step is at least epsilon, so the maximum number of steps in the path would be C star divided by epsilon. And so that gives you an upper bound of how many nodes in the worst case, you would have to expand. And the same thing for the space complexity. And it is optimal in terms of finding the shortest distance path. Okay. So are there any questions about this? Yeah? Good question. Okay, so the question was, is this the same as Dijkstra's algorithm? Okay, very good question. So this is uniform cost search. Dijkstra's algorithm, it's pretty much the same. The only, it would be, the easiest way to answer this question would be to show you how these things are implemented in Prolog. Look, let me come back to your question, because I've got, I'm going to show you some Prolog code for implementing these algorithms, and the simple answer is that Dijkstra, the standard uniform cost search, if it keeps searching, it'll find a series of paths. After it's found the shortest cost path, then it'll find the next shortest and the next shortest. And you know, with Prolog, you can hit the semicolon and get more and more paths that are just of increasing length. Dijkstra's algorithm uses a slight trick which enables you to get the first answer faster or using less memory, but then you lose the ability to find the second longest and the third longest and the fourth longest, which usually you don't care about anyway. Okay, so that's the short answer, but when we look at the Prolog, you'll understand why that is. Yeah, very good question. Okay. Right, so breadth first uniform cost search. So then we move on to depth first search. Now, depth first search, again, I just show you this, try to show you this graphically, if I can. Yeah, so if you I urge you to go and watch this little video that I've prepared because I go through the whole history of Ariadne and the Minotaur. So what's this algorithm kind of mimics the way you would probably explore the maze yourself if you were physically located in the maze. So let's say you start in Arad and then you're just wandering around, so you go to Zerind and then you go to Aradia, and we assume that you're unwinding a red, you're unwinding a ball of red string as you go to try to remind yourself of where you came from. So this is this goes back to Greek mythology. Theseus and Ariadne. So there was this allegedly a dungeon underneath the Minoan palace in Crete, and the Ariadne's boyfriend, there was a monster down there called the Minotaur who was half man and half bull, and Ariadne got her boyfriend to go into this labyrinth and find the Minotaur and kill it and then come back, and he unwound this string as he went. And this is very, the word clue, the English word clue, actually the meaning derives from a very old-fashioned word for a ball of string. So okay, so he goes up there and then here, but then it's possible he may come back to where he's been before, but then because he sees the string, he knows he's visited there before, so he needs to backtrack, right? Okay, that's no good, and you have to kind of remember, if you can, you try to remember that you've already taken that path, so you don't need to take it again. And then you explore somewhere else, so you don't know where the goal is, so you're just wandering randomly, so you might come all around here and get back to Arad again, and then you know that that's somewhere you've been before, so you backtrack here. You keep backtracking until you have somewhere where you've got an alternative path, which is here, and then you may go back there and see that you've been there before, so you block that off, and eventually you get to Bucharest. So this is how the depth-first search works. Now, what's the advantage and what's the disadvantage? Well, the disadvantage is that you don't necessarily find the shortest path. You're just wandering around randomly. So here we found a path which is quite long compared to the shortest path. That's the disadvantage. Now, what's the advantage? Well, the advantage is you don't have to remember too much when you're exploring. So, in this case, I've already explored all of these cities, but I don't have to keep those cities in my memory. All I have to remember is that I took this path here and it led to a dead end. Right? So, the only things I have to remember the sequence of cities along the path that I'm currently considering. I have to remember, for each of those cities, I have to remember all the paths, all the tunnels coming off that city, and among those I have to remember which ones I've explored and which one I haven't explored. That's the only things I have to remember. And in a simple case like this, it doesn't make much difference, but if we're talking about a big problem like Rubik's Cube, this can save, well, Rubik's Cube is not a good example, but there are some situations this can save you an enormous amount of memory. Okay. Now here's another graphic just to try to illustrate the same point. Let's imagine that so this is a tree which is where every node has the branching factor is 3 and every node has exactly 3 children. If I'm exploring this tree by depth first search, obviously I'm going to go through all the nodes in order from left to right, but if I'm currently exploring this path, this is the only information. I've explored these nodes, but I don't have to keep them in memory. I can erase them from my memory. And when I get to here, I can erase these nodes from my memory. And someone pointed out to me I should actually use different colors to show I should have used different colors here to show what I have explored and what I haven't explored. So this I have explored, this I haven't, and so on. But you get the idea. The idea is you can get away with storing very little in memory. Here I've thrown away all of this from my memory. Okay, so what are the properties of this? Well, the thing about depth first search, it's very important that we don't go in a circle, so that we remember where we've visited before or the nodes along the current path, because if I didn't remember that, I could go from Arad to Zarind and then back to Arad and then back to Zarind, and I could just keep going endlessly back and forth between Arad and Zarind. Okay, so I need to, so with breadth first search and uniform cost search, with breadth first search, removing those cycles saves me time, but I would still find the solution anyway. With depth first search, I have to make sure I remove the cycles, otherwise I might never find the solution. Okay, so that's just a little kind of tweak there. So you have to assume that you avoid repeated states along a path, and then the thing is complete. Eventually it will find a solution. Now, what about the time and the space okay, is it optimal? No, as we saw, it can find a suboptimal solution. The time complexity can be very bad. It's not b to the d, it's b to the m, because it could explore every node in the search space, not just let's say there's 10 nodes in the search space, but there is a path of length 4, it might not find the path of length 4, it might explore all the paths of length 10 almost. Right? So if it's not optimal and the time complexity can be bad, why do people bother with this? Well, the big advantage is this space complexity. The space is linear. Now, just again, I'm just pointing out these kind of details. If you look online, some sources online, perhaps even Wikipedia, will say that the space complexity is order m rather than order b times m, and maybe it's worth just explaining how they arrive at that. So the reason I say that it's b times m is because I have to remember that, so at this point I've got to make sure I don't explore the same thing twice, so I have to remember that I've explored this but not that. I have to remember that I've explored these two already, and I have to remember that I haven't yet explored these two. So the reason we say is b times m is because for every node along the maximum length of that path is m, and for every node along the path there's b branches, and for each branch I have to remember yes or no, have I explored it or not. That's where we get the b times m. Now the people who say that it's order m, well, there are some puzzles where you can agree on a predefined order of the actions. You know, so if I'm searching the 8 puzzle, I could decide, okay, I'm going to first, the order in which I'm going to search this is I'm going to first move the tile above the blank, and then the one to the left of the blank, and then the one underneath, and then the one to the right. Or I could decide I'm going to base it on the number that's on the tile. If there's a lower number, I'm going to try that first. So if I have a convention that tells me the order in which nodes are going to be explored everywhere in the tree, then I wouldn't have to remember which ones I've explored and which ones I haven't. So that's why they have the M. So the two, but both things are kind of valid. It doesn't really make much difference. The bottom line is that it uses up very, very little space compared to other algorithms. I don't know what happened to my lecture notes. That's very weird. Okay, any questions about this? Where are we? Okay. Just two to go. Just a couple of things to go. So iterative deepening search, depth limited search, and then iterative deepening search. Okay, now depth limited search says, okay, it's the same as depth first search, but I'm going to limit the depth. There's a certain depth k, and I'm not going to explore any path longer than depth k. So I don't really have a separate graphic for this, but this graphic could serve that purpose because you could imagine that this is part of a bigger tree. The bigger tree exists, but this is only the part of the tree that I'm exploring. Okay, I'm just going to explore this, and I'm not going to expand any of those nodes there because I'm cutting myself off at depth 3, right? So in that case, you could regard this as a graphic of depth limited search. Oh, there it is up there. Okay, no, that's not it. There it is. So depth limited search, it's not... is it complete? It is complete so long as the solution lies... It is complete so long as there is a solution within the depth that you're searching. The time complexity, because we're cutting the search off at depth k, the time complexity is now b to the k instead of b to the m. The space complexity is b times k. It's still not optimal. Obviously, it'll find a solution of depth less than k, but it might not be the shortest. And then finally we move on to iterative deepening search. So this, what happens here, and maybe this, I'll go back to the full graphic here. So let's say, so this is the way iterative deepening search works. So I say, okay, I'm going to first do a depth first search to depth 1 to see whether there's a path of length 1 to the goal. If I don't find the goal, then I start again and I do a search to depth 2 using depth first search. And if I still don't find the goal, then I start again and I go to depth 3. And I keep going. If I haven't found it, then I go to depth 4 and then to depth 5 and then to depth 6. And this is called iterative deepening search. Now, you notice, let's just look at this particular graphic here because this helps us with the analysis. So here, the branching factor is what? 3. And let's assume, okay, the branch factor is 3. Now, when I carried out this process, you'll notice something. This root node got expanded 4 times. And because it appeared at every step, these nodes got expanded 3 times, and these nodes got expanded twice, and these nodes only got expanded once. Okay? So in general, again, yeah, the same sort of graphic here. Like, okay, is it complete? Okay, first of all, is it complete? Well, yes, because you're searching to depth 1 and then to depth 2 and then to depth 3, and if the shallowest path is at depth D, then when you get to depth D, you're going to find it. Yeah? Now, what about the time complexity? Well, if we did depth limited search, the time complexity would be the same as for breadth first search. So it's this geometric progression, which we already said is order B to the D. Now, when we do iterative deepening, this is if the solution is at depth D, the root node will be expanded D plus 1 times. Nodes that are 1 step away from the root will be expanded D times, and then D minus 1, and so on. So you get this summation here. Now you can actually, if we assume the branching factor is bigger than 1, otherwise you wouldn't have a tree. You'd just be exploring like a bamboo stalk. It turns out that this is order B to the D. You can prove this using generating functions or other ways, but rather than prove it formally, we just look at an example that kind of illustrates this. So let's suppose that the branching factor is 10 and the depth is 5. So this is not unreasonable for, we talked about Rubik's Cube, the branching factor being 12, so this is 10. So if we were to do depth limited search, the number of nodes expanded would be 1 plus 10 plus 100 plus 1,000 plus 10,000 plus 100,000. So this is like 111,111. So that's if we knew in advance that the solution was at depth 5 and we just did a direct depth first search, depth limited search to depth 5, that's how many nodes we would expand. Now, if we do iterative deepening, it turns out that, so you expand the root nodes 6 times and each of the first nodes 50 times and so on. So the number of nodes is actually 1, 2, 3, 4, 5, 6, which is only 11% more. So this is really the important thing. If the branching factor is high, almost all of the search effort goes into the last stage. So if the solution is at depth 5 I'm going to spend almost all of the time doing that search to depth 5. The searches to depth 1, 2, 3, and 4 take very little time in comparison. So at first, this algorithm looks like you're wasting a lot of time, but in fact, you aren't. In fact, if with a low branching factor, you would be wasting a lot of time. But if it's a high branching factor, you're only spending a little bit more time compared to breadth first search, but a lot less memory. So this algorithm is a very good compromise between breadth first and depth first search. It has it combines the advantages of both. So like breadth first search, it's complete and optimal, but it has the very low memory requirements of depth first search. So among the uninformed search algorithms, this is probably the best one. And when we get to games, we'll see that this is also used in game tree search. Yeah. Any questions about this? Yeah. And okay, finally we get to bidirectional search. Now, what happens with bidirectional search? Well, this is if you know in advance what the goal state is, well, you may notice, in those little kiddies' books, like, you're waiting in a doctor's waiting room or something, and the kids do those little puzzle books, and they often have a little simple maze, and kids often figure out pretty quickly, sometimes they can solve the maze faster by starting at the end and working back to the beginning rather than the other way. Well, bidirectional search kind of plays on that idea, but you do both at the same time. So you start to search out from the initial state, but simultaneously you try to work backwards from the goal state, and you hope that they'll meet in the middle. So you've got a tree, you've got two trees, one expanding out from the start state and one from the goal state, and then when it turns out that one of these leaves is the same as one of these leaves, then you've created a path from the start to the goal. And this is called bidirectional search. Okay? Now, this is actually, why is this fast? Well, let's suppose the branching factor is 10 and that the length of the shortest path is 10. So if you did breadth first search or iterative deepening search, the number of nodes you would have to expand is 10 to the 10, right? So that's 10 billion. But if I do bidirectional search, this tree will have depth 5 and that tree will have depth 5, so I've got 2 to the 5, which is 100,000 nodes here and 100,000 nodes here. So the time is actually 200,000 instead of 10 billion, right? That's a huge speed up. So in general, this algorithm has order b to the power d over 2. Right, which is the square root of what would happen with breadth first search. Yeah. So in the right circumstances, this can be a lot faster. Now, there's a couple of caveats about this. First of all, we have to have a way of searching backwards from the goal. So there could be multiple goals. Since for some puzzles, there could be multiple goals, and you don't know which one you're going to get to. So you wouldn't be able to do this. Or sometimes it's impossible to work backwards. So things involving physical simulations, if I've got if I hit a pool ball, if I'm playing pool or snooker and I hit a ball, I can use physical simulation to figure out what's going to happen when it hits the other balls or whatever, but it may not be possible to do that physical simulation in reverse. So there are some situations where you can't use this, but in cases where you can, it could save you a lot of time. The other thing is, for those of you who know about data structures, every time you generate a node here, you have to have a fast way of checking whether it's the same as one of these nodes. So you could use a so if you use a hash, this is theoretically if you use a hash table with a good hashing function and so on, you should be able to look that up in constant time. In practice, you may have to resort to a skip list or something that's log, where the lookup time is logarithmic. Yeah, so that might slow it down a little bit, but it's still going to be a hell of a lot faster than breadth first search. Okay. And this is the table that summarizes all of these properties. Just one final thing and before we take a break. This time complexity of breadth first search, sometimes people write b to the d plus 1 here instead of b to the d. So normally to keep things uniform, we don't check if something's the goal until we're ready to expand it. So if you did that with breadth first search, the time complexity could be b to the d plus 1, but with breadth first search, as soon as the goal is generated, you actually know that that's the shortest path. You don't really need to wait for it to be expanded. So you could speed breadth first search up a little bit by stopping when the goal is generated instead of expanded, and that reduces it to b to the d. So there's a couple of little kind of subtleties here, but it doesn't really make much difference. It's exponential in the depth. Good. Okay, are there any questions about this? Okay, let's take a 5-minute break, and then I'll show you the Prolog code, and then we'll move on to some heuristic search. Yeah.
Yeah. In terms of this two.
Yeah.
In terms of this two, what if my input is only one, like this? What if my list is only 8, one element? So my result is that I will output this result. So is this okay or it's better?
This one is correct.
This one is correct. And as for this, this one question about the tree. I got a solution if the tree is empty.
Yeah.
But do I need to consider this situation if someone in this is nothing, just nothing? Do I need to consider about this situation?
No.
It
has to be a valid tree.
Okay, so
you should just say false or something in this case. Yeah.
I tried it when I operate this code.
Yeah.
If I type in this kind of thing, it just turns out some error.
Yeah, well, that's because the number of arguments is wrong.
Yeah.
So you don't have to worry about that.
Okay.
Yeah.
And last thing is that I think there is prolog missing behind it because when I run it and
okay. I should put prologue at the end. Okay.
Yeah, because when I run it in the VLAB,
yeah.
It can't see the.
Okay.
Yeah.
Good point. I'll correct that. Yeah.
Okay, that's all. Yeah. Okay, thank you very much.
So I raised my hand a few times, but I guess he didn't acknowledge me. So
Oh, sorry. Yeah.
We made a list of all the questions.
Oh, yeah.
So why is DFS considered to be incomplete?
DFS. I think it's just if you have to, if you check for repeated states, then it becomes complete. Yeah. Oh, what did it say at the end? Oh, that's a good question. Yeah, I'll try to update this. It actually...
So is it complete or not?
Optimal. If you check for... as long as you check for repeated states along a path, then it is complete. Yeah. I should have put that as a note here.
Yeah. So in the case of like breadth first search, you're still sort of looking at the same paths. Like you start from the city 1, city 2, city 3, and then you go to city 2, and then you could go back to city 1. So
right.
That's also a possibility in DFS. So why is that complete, and why is DFS incomplete?
Well, with breadth first search, if you consider these ridiculous paths that go back and forth, breadth first search will still find the solution because because it searches depth by depth. The ridiculous paths will slow it down, but won't prevent it from finding the solution. Or with depth first search, it could actually prevent it. Yeah.
Okay.
So in one case, it's just like a speed up. In the other case, it's like the difference between whether it finds the solution at all.
Sure. Yeah. And can you use DFS, BFS, or the iterative algorithm when the distances between cities are considered?
Good question. So BFS, well, with the distances between cities. Okay. Well, with BFS, if you consider the distance between cities, it becomes uniform cost search. With DFS, the question doesn't really make sense. With iterative deepening search, yes, there is a version of iterative deepening search where you set a certain distance and you do uniform cost search, but you do depth first search, but you cut yourself off at a particular distance, and then you increase the distance. So don't normally. That's right, yeah. And when we get to A star search, there's also like iterative. So there is such a thing as iterative deepening uniform cost search.
Okay.
And there's also iterative deepening A star search.
So out of all the algorithms that we covered today, what would be the most efficient way to figure out the search problem when you take distances into account?
What we've covered so far, iterative deepening search is best, but if we take into account the heuristic, then probably iterative deepening A star search is the best.
And so what does B mean? Like different depths of the trees can have different nodes, different number of nodes?
Yeah, but normally we just say what's the global,
Like maximum?
what's the maximum branching factor? Yeah.
Okay, all right. Okay. And what is M in DFS?
That's the maximum possible depth of the tree.
Okay.
So
I thought that was D.
No, D is the depth of the shortest solution, which you might not know in advance.
Yeah.
But M you probably know in advance. So if it's a graph and you're eliminating repeated nodes, it would be the number of nodes in the graph.
So in what situations would you use DFS over the other algorithms?
Good question. That's one of the tutorial questions. Yeah, maybe you should have a think about that, and we can talk about it next week or in the tutorial.
And so when you're discussing the Rubik's Cube, how many number of states will it have?
I'll say more about that when we get to the heuristic part.
Because I was thinking 27 because it's a 3 by 3 by 3 sort of thing, so you could map each.
Oh, but the number of states is exponentially large.
So is a state supposed to be the different permutations of colors that exist on each side of the cube?
That's right.
Okay. Yeah, then it's really large.
Yeah.
All right. Okay. Thanks a lot.
Sure.
Students told me
I
permission denied when they run the
permission denied.
Yeah. But they told me this Monday, so I think it's solved.
Oh, I hope so. Someone was saying maybe we need to put prologue in there, but yeah, okay.
Oh, just add a prologue.
Yeah.
Oh, I got it. Could you give me an example of the episode agent?
Episodic. Oh, well, I was saying medical diagnosis. It looks at a scan of one patient and makes a decision, and then the next patient is completely.
I see.
Yeah,
I just got stuck with this question.
That's okay. Yeah.
Awesome. Thank you.
I like to ask, but not in uniform costs.
Yeah.
Do I need to expand all nodes at a certain depth before going to the next level?
No.
Or no?
No. It's all based on the distance, the path length.
So if here is 200 and here the sum is less than 200, I move here and then I move here.
That's
later?
right, exactly.
Okay,
Yeah.
so I can, because I'm trying to do this and I think it doesn't work. Maybe it's because of this.
Right.
Okay, and then while we're referring to deep first search, is it the same thing of the iterative learning? Because I don't know. Because when he was talking about this, he refers to the other one, to the iterative deep search. They are different.
Yeah, they're different. So depth first search, you don't have any maximum depth that you're searching to. So you could find a really, really long path.
Okay, sure.
Yeah.
And this one here is the one that you every time need to come back to.
That's right. Yeah, you cut the search off at a certain depth.
Okay, and what about this? We told that we cut off at a maximum depth, and it's complete. But if our depth is not enough deep.
Yeah, it's only complete. Right. Yeah, it's a funny. It's complete. If the solution does exist within that depth, then it's complete. Otherwise, it wouldn't find it. Yeah.
So for example, in depth 3, Bucharest is not find. It's not complete.
That's right.
Oh.
Yeah. So maybe I should have put that. It depends what we mean by complete. If the solution is there within that depth, it will find it. Yeah.
Okay.
Yeah.
Simon, question 5.
Yeah. The empty tree should be considered a heap, I think, yes.
That would be the base.
You probably need 2 base cases, I think. You probably need, I don't know.
I don't know, does every single node come down to an empty at some point?
I don't know. For some reason, my solution has 2 base cases. One is the empty tree, the other is the single element tree. You probably, whether you can get away without that, I'm not sure. But
Because every single element would have either another element below it or an empty.
you might get away with 1 base case, but just try it and see. Yeah. Yeah.
Submit the test. It means the test is passed. It doesn't mean that it's correct.
No, you should try to do your own testing as well. Yeah. Other examples.
In terms of the structure of the course,
Yeah.
the next 1 or 2 assignments after this will also go through computers?
The second assignment will be a written. Well, the second assignment won't involve writing code.
Okay.
It'll involve some written part and maybe running some code and
Right. Okay.
reporting on the results. The last assignment will be programming as well. Yeah.
Okay. In terms of this current assignment,
Yeah.
I emailed the admin.
Oh, yeah.
Yeah, about possible extension because I'm not going to be 2 weeks.
Oh, yeah.
They haven't gotten back to me on that.
Oh, okay. Look.
I have a letter from Cedar.
Yeah, look, maybe just email me directly. It's possible the email redirection is broken or something.
They haven't emailed me back about anything, and I'm like, have they got it or have they not?
Okay, I don't know whether the admin addresses
Yeah.
will, for those courses, work or not. They've been fiddling with the mail system, so yeah, just email me directly.
Does this course estimate marks for certain areas? 'Cause
you'd think you can't. It'd be better if it's just.
well, I know that I can do the first two, but the
Yeah.
third one's falling in a time period where I'm going to assume the third one's going to fall into.
The third one. We don't usually give an estimated mark for the third assignment, but if you can do, we sometimes extend it to after the exam or something. In extreme cases, maybe you can submit it after the exam or something. I mean, just email me and we'll try to sort something out. Yeah.
Do you have some example code, like the tree about tree?
Oh yeah, I'll show you some code now about to do these searches. Yeah. Oh, you mean the tree
yes,
stuff?
Last week lecture.
Oh
I
yeah.
cannot find a code, example code.
This link should be on those. Okay, I'll have a look. I think the link should be on the. Where is it? What is it?
The tree. Middle one. There don't have the example code.
Okay. Backtracking. The tree. Where is the tree? Well, there's some code here.
Yeah, but I don't know how to write into the PL document.
Just copy and paste this into a PL something.pl.
Yeah.
And then you can run it. Yeah.
But there's some problems, so I don't know what is the. So it will be some error if I type some.
I don't know, just create a file called tree.pl.
Yeah, I know.
And copy this into it, yeah.
But if I code some kind of things, it will give me some error.
Maybe send me an email, tell me what error you get, or go to a lab session, yeah. And then
Thank you, sir.
Question regarding the tutorials.
Yeah.
So before the tutorial, are we supposed to go through all those questions and post it on Open Learning? Because I saw some people
it would be best if you do that, yeah.
Is it after the discussion in our tutorial session we post the answers?
You can do it either before or after, but it's good to have a go beforehand, yeah.
I was working on another about the depth limited search.
Yeah.
I don't really understand why it would be useful. As in, we would always know the breadth of a search, right? Like Rubik's Cube.
Depth limited search. The only reason we teach it is it's a stepping stone to depth iterative deepening search. It helps us to explain what iterative deepening search is. Yeah.
Prior to a problem, we won't know if the solution.
You wouldn't know where the depth. Exactly. That's right.
If the answer is 4 depth and I set it as 3, like I'll not get the solution at all.
That's right.
So the only reason in practical applications it is not used at all.
That's right. Yeah.
I had a late enrollment on last Friday.
Ah, yes.
So what should I follow? Just your notes or to catch up with your lectures?
Yeah, try to look through the notes and do the prologue exercises and start on the assignment. And when you have time, go back and look through the videos on the website. Yeah.
Okay. So assignment is about what, like?
About prologue. Yeah, it's similar to the prologue exercises.
Okay, thank you.
Good, so I think we need to start again. So first of all, if you click on Learning Activities and go to the week 3 module, we've created this widget called Fun with Mazes. And I strongly encourage you to go and have a look at this. There's 2 versions of this. The week 3 module includes the uninformed search strategies, and the week 4 module includes the informed search strategies, but otherwise the interface is the same. So you can choose a type of maze and then generate random ones, and then you can choose a search algorithm, and you can actually watch the thing apply that as search algorithm to that maze. So we hope that this will give you a kind of tangible way to understand the relative advantages and disadvantages of the different algorithms. So this is depth first search going on one of these concentric tree mazes. If I look at a concentric graph maze, there's a few more holes there. So now I'm doing breadth first search, and you can kind of see those pink nodes are the leaves of the tree, and it kind of searches in parallel. This concentric one is maybe not such a good example. Let's look at something else, maybe just a graph maze. Now, by default, it always generates this with the start node in one corner and the goal node in the other. So this shows you breadth first search on this kind of maze. So you can see how it's actually expanding out the paths in order of their length. If I switch to, say, depth first search, it kind of goes in a random way, and sometimes it kind of explores a lot of really long paths. That found a solution in a reasonable time. If I run this again, oops. I think we've set this up so that it'll take a different random path each time you run it. Yeah, so this time it's gone off in that direction. So you can generate mazes and run these algorithms. But in addition, you can create your own mazes. So we've got an editing tool here. Yeah, see, this is an example where depth first search filled up almost the entire maze. Let's have a look at bidirectional search. So here you can see bidirectional search is searching from both sides simultaneously, and then eventually they kind of meet in the middle. Now, let's see how we can create our own maze. So you can start with a randomly generated maze or just alternating squares or even an empty maze, and then I can click on these things and either add or remove walls at my own discretion. So let's try to do breadth first search on this maze. And then if I want, I can move the start and the goal node. So the tutorial question, so have a play with this. The tutorial questions ask you to try to devise mazes for which certain, breadth first search works faster than depth first search or different things like this. You can also, so for example, let's say I move the start node into the middle, and then I get rid of, I create some more, let's say I create a lot of goal nodes, and then I kind of remove some of these, whoops, what's happening there? I remove some of these walls. So you can sort of have a bit of fun with this and create your own mazes, and I better remove that goal in the middle because otherwise it'll just fine. Okay. So you can create your own maze and then have a go with this. So, depth first search, it can find any one of these red guys and they're all kind of equally good. And this is breadth first search on the same problem. Now, if that's interesting. Okay, it found that solution there. Now, if I want to do bidirectional search, I think it refuses. If I have multiple goals, it refuses. So I would have to make sure I have only one goal. So let me put the start. Let me just let me just go with alternating squares. Let me put let's say the goal node is here and the start node is here, and we get rid of that other goal node there, and then we try to do bidirectional search. So here you can see a case where bidirectional search might be a little bit faster than it's to get to see the full benefit of bidirectional search. You have to go to a high dimensional problem. But I think you can see this is a little bit faster than if we did, for example, breadth first search. So please have a go at that. Discuss it in your tutorials and post to the forum and see if you can come up with something creative. Okay, good. Now the other thing is I want to show you, I've provided some Prolog code for you. So this is, oops, where is it? Now, and you can download this and run it. There's some instructions here how to do that. So you click on this button and you download it as a zip file, and then if I run Prolog, let's see. It creates these files here. So all these, I've implemented all of these now. And then there's, so this Romania.pl just simply lists the roads between different cities and tells you what the goal city is. And then we've got stuff like puzzle 15. This is like the 8 puzzle or the 15 puzzle, and it tells you the start state and the transitions, but not just listing them explicitly, but rules to generate what position can be got from another position. And so if I run this, I run prologue. So if I type Romania, that means it'll load all the facts to do with Romania. And then if I type breadth first, okay, so then the way this works is I type solve Arad sol gn, and it comes back and that says, look, I want you to look for a path starting from Arad, going to the goal state. I want the path will be called sol, the number of nodes will be called g, and the length will be n. So it comes back and says, n is the how many nodes were expanded along the way. So this says, okay, I expanded 10 nodes, I found a path of length 3, and this is the path. Now if I type semicolon, it'll keep finding longer paths. So, okay, if you don't like that path, you can take this path which has 4 nodes, or this one which is length 5, and eventually it'll find all possible paths which don't have cycles. The code is written in a way that avoids cycles. So that's every possible path from Arad to Bucharest without cycles. So have a go with this as well. Now, let's just have a quick look at this code. Let's see. So this is, so how does this solve thing work? Well, so this is getting to be a little bit, it's similar to the constructs that you've been looking at in the tutorial and in the labs, but taking it sort of to the next level. So this is recursive. So this is the base. Let's have a look. Okay, so solve in this case says, okay, I want to do solve by applying breadth first search. I start with just the start node, and I want to find a solution. So this is the base case. If right, so I've got a list of paths to be expanded, and if one of them, if the path, they're in reverse order, the paths are in reverse order from the goal back to the initial state. So if the first if the first node in the first path is actually a goal, that means I've solved the problem. So this is the solution, and this is the length of it. And then this is the recursive case. So it says, okay, I take the first path in the list and I extend that path to create possible new paths, and then I put those new paths at the back of the list, and then I do continue my breadth first search on that new set of paths. And then I have to define what it means to extend a path. Well, I find all nodes, I look at the first path in the list, and this node is the leaf node of that path, and so I look at all ways that I can expand the node. So if I do an action, this S means that there's a step that takes me from this node to that node, and if it exists, then I extend this path by adding that new node onto the front. I check to make sure the new node is not already in that path, and that gives me a set of new paths. Okay, so this is the entire, this is like, this is the beauty of Prolog in a way, that with very short code like this, you can implement the whole algorithm. So that's breadth first. Now, if we look at some of the others, okay, UCS Dijkstra. Okay, so you were the one who asked the okay, so this code is based on code that a colleague of mine, I think originally came from the textbook, but what it did was it stored all of the paths as a list. So it kept in memory a list of all the possible paths, and the problem is it ran out of memory. If you do something even like the 8 puzzle or the 16 puzzle, it would run out of memory. So I replaced it with a new version. It doesn't store a list of paths. Whenever it generates a new segment, it just keeps a list of where of pairs that says that this node leads to that node. So when you go through to reconstruct the path, you have to do it piece by piece. You say, okay, this node came from that node, then I'm going to look through the list to see where that node came from and where the previous node and the previous node. And that saves a lot of memory and stops you from running out of memory. So you can, again, you can have a look at this. It keeps this list of kind of legs, and once you've found the goal node, you have to go through and try to build the path to take those legs, piece them together to make a path. So this was, maybe I just go back to, where was this UCS? Search. Right, so this was Dijkstra's innovation. So let's say, we're trying to find an example where something, it only stores, so what Dijkstra figured out is, well, I don't really need to store every possible path. For every city, I just need to remember what's the shortest path to that city that I know of, and which city I came from, right? And then if I find a shorter, if within the search I find a shorter path to that city, so at this point I've found this path to Bucharest through Fagaras, so I would have a little segment that says that, okay, I've got a path to Bucharest that's 450 in total, and the previous city is Fagaras. Now, if I keep searching, then I find a shorter path. I say, okay, now I know a new path that's only 418 that comes through Pitești, so I throw away the previous one. Yeah, I don't keep it in memory. Yeah, previously I had this 450 in memory. Now I've thrown that away and just kept the 418. So that can save me a lot of memory. But as I mentioned, the downside is, and it'll find me the shortest path, but then the downside is if you ask me what's the second shortest path or the third shortest path, I have no idea because I've thrown away that information. But I don't care, I just want the shortest one. Yeah. Okay, so just, have a look at this. This, like I say, this is sophisticated Prolog. It's beyond what you would be expected to be able to write, but I think it is useful to go through and try to see how this works. Okay. Any questions about this? I know quite a bit of material for one day. Now, okay. So just to recap, all the algorithms we looked at so far follow this pattern. We have a queue of nodes to be expanded. We start with the queue just consists of the initial state. Then we repeat this cycle of taking a node out of the queue, testing if it's the goal state, otherwise expanding it to generate successor nodes and adding them back into the queue until we find a solution, or until the queue becomes empty, in which case there is no solution. So with depth first search, all the new nodes were added to the back of the queue. So this is a traditional queue like you see when people are queuing up at the bank or the post office or the railway station or the bus stop. With depth first search, one way to implement this is that all the new nodes get added to the front of the queue. So that means when you generate a new node, that node will be expanded before any other node. Right? So this is actually a stack rather than a queue, for those of you who know about these data structures. Now, most of these searches fit into what's called there's this phrase best first search. Best first search really just means that there's some function of a node and that function tells you which node you're going to expand next. The one with the smallest value of the function is the one you're going to expand. And one example we've seen of this is uniform cost search. So it's traditional to use G of n to indicate the length of the path from the start node up to that node n. So you look at the nodes you've got available, you calculate G of n for all those nodes, and the one that's smallest is the one you expand. So now what we're going to talk about is search strategies which also include an estimate of how far you are from the goal. Right, so we assume that you have some way of telling whether you're close to the goal or not. You might not know you can't tell the exact distance from where you are to the goal, but you have some idea. And so we're going to look at greedy search. With greedy search, you just pick the node that you think is closest to the goal and expand that one. And then we have A star search, which combines the path cost up to that node plus the estimate of the path from that node to the goal. So we'll look at these two. Right, so now I'm going to add even more information to the map. So first we just had the lines, and then we had the distances of the lines, the length of the lines. Now I'm going to tell you what's the straight line distance from each of these cities to Bucharest. So this gives you some idea how close each city is to Bucharest. So the driving distance, if you look at, for example, Pitești, the straight line distance is 98, but the road is 101. So the road distance is always a bit longer than the straight line distance. Făgăraș, the distance is 178, but the road's actually 211 because it has a few twists and turns in it. So this gives you some estimate, but it's a little bit less than the actual driving distance, which is the thing we want to minimize. So this is an example of what's called a heuristic function. Now, the word heuristic is very overused in AI, but here it has a very specific meaning. It means that it's a function that estimates the distance to the goal so it's a function for each node. It gives you a value that's like tries to guess how far you are from the goal state. And this can help us to search faster, right? So there's this thing called greedy best first search, or often just greedy search. It always expands. When it has to pick a node to expand, it always picks the one that's closest to the goal. Okay, so again, let's have a look at some of these graphics. So here we start out the same way, but then when we want to pick which node to expand, we don't pick, we pick the one that we think is closest to Bucharest. So you could look at the numbers, but from looking at this picture, it's, you can see that Sibiu is the closest distance to Bucharest. So that's the one we expand. And then from here, Fagaras is the closest one to Bucharest. So we expand that. Now, so one way to think about this, so if you go back to the uninformed search strategies like breadth first search and depth first search, breadth first search and iterative deepening search, they will find the shortest path. They will find the solution, but breadth first search is guaranteed to find the shortest solution, but because it has no idea how close it is to the goal, it will explore every possible path that's shorter that's closer than the goal. So if you think about a case like Rubik's Cube, we said the branching factor was 12. In a typical situation, it may take 17 moves to solve the cube. So breadth first search would explore every, if this is 17 moves away from the goal, breadth first search will explore every possible sequence of 17 moves in order to find the solution. So it'll explore 12 to the power 17 states, which is like larger than the number of atoms in the universe. So you think of you think of this as like an expanding balloon that's just expanding out equally in all directions until randomly it bumps into the goal. Now, what these heuristic searches do is they guide the search and preferentially expand nodes that they think are closer to the goal. So you can see this circle has been stretched out into a kind of sausage shape, and most of the time that will find you the goal much faster because you're preferentially expanding nodes closer to the goal. Okay? But notice it didn't, so it did find it, and this is typical behavior. Normally, normally greedy search does find a solution very quickly, but it doesn't find the best solution. So here it's found this solution here, but we know already that this one here is a little bit shorter. Okay. So this is the example of best greedy search, and these numbers indicate those straight line distances. And you can, here's some examples you can have a look at for yourself to see how this works. Yasi to Fagaras, and so this is sort of a funny thing here. If you start in Iyasi and you want to go to Fagaras, you would start out by going to neemt because the straight line distance is shorter, but then you'd realize that's a dead end and you'd have to go back the other way. So what are the properties of this? Well, again, we get this issue about loops. If we don't check for repeated states, then we could just go back and forth between neemt and Yasi and never get any closer to the goal. So you have to check for repeated states. Once you check for repeated states, then it will be complete. The time complexity in the worst, right, so the thing about this greedy search is in most cases it does find a solution quickly, but in the worst case it may take a really long time. So if you look at it in terms of the worst case situation, it could be just as bad as depth first search. And this is, I think, one of the tutorial questions maybe for the following week is try to devise a maze in which will be bad for greedy search, which will make greedy search actually, take a long time. The space complexity is high because it has to keep, in the worst case, it has to keep all its nodes in memory, and we've already seen that it's not optimal. It can find a longer path than the optimal one. Okay, well, we already talked about uniform cost search. Okay, so then we get to A-star search. Now, A-star search is like the star of the show. This is the optimal algorithm, what we call technically an optimally efficient algorithm. So this is, of all the algorithms from today, this is kind of the best one, right? Now, let me try to explain the motivation for this. So let's look at what happened with greedy search. The problem with this is the reason it found the suboptimal solution is because it expanded Fagaras. It chose to expand Fagaras instead of Rimniku-Vilsia. Now, because Fagaras is closer to Bucharest, so that's why it's called greedy search. Is it thinks, if I expand Fagaras in one step, I can get so close to the goal. So it's always trying to kind of bite off the biggest piece of the puzzle that it can. It's trying to get as close to the goal as it can as quickly as possible. But in doing so, it ends up finding a suboptimal path because, yes, Fagaras is closer. This part of the path here from Fagaras to Bucharest is shorter than for Rimniku-Vilsia, but the path, what we're trying to minimize is the entire path from the beginning to the goal. So the path consists of two parts. There's the part we've expanded already to get to this node, and then there's the rest of the path from that node to Bucharest. So this node is further away from Bucharest, but it's closer to the initial state, right? So a more intelligent approach would be to add these two things together. We say, okay, I look at the distance I've traveled already to get here and add what I think it'll take to get to Bucharest, and I do that for this node and then do it for this node. And when you take that approach, this node comes out a little bit ahead because this part of the path is shorter, and so the whole thing is shorter. So that's the motivation for this A-star search. So what it actually does what A-star search actually does when it tries to decide which node to expand, it looks at a combination of these two things. So it looks at the cost of the path to get from the initial node to that node n, and then the estimated cost to get from the node I'm at to the goal. It adds those two things together. You get an estimate for the total path from the initial state to the goal state through that node. So let's just look at an example of this. Okay, so here's the same point that we reach where we're trying to choose between Fagaras and Vimnicu-Vilsia. So these numbers here, the font is so small, but these numbers here indicate the sum of this distance plus that distance. For Fagaras it's 417, and for Vimnicu-Vilsia it's 413. So it slightly prefers Vimnicu-Vilsia. And then Pitești, but then we still, okay, so this is the same thing but without the map, and you can see the numbers better here. So when we combine G of n and H of n, this Vimnicu-Vilsia is a little bit lower. And then we expand it, and then Pitești is 415 compared to 417. And then we get to Bucharest. Now again, we have this issue. We can't stop yet because we know we have a path to Bucharest which is 418, but our current estimate of the path through Fagaras is 417. And so we have to expand. It's still possible there may be a shorter path going through Fagaras. So we have to expand Fagaras. And but then we find that this path is longer than that one. And in fact, every estimate here is bigger than 418. So that's the point at which we stop the search, and we know that this is the shortest path. Yeah, I'm sorry, I'm not. I think if you go and look at the videos, you'll get a better understanding of this. It includes all the details. Okay, now why is this guaranteed? So it is complete and it is optimal. Now, to understand, let's try to understand why it's optimal. So, we can prove that it's optimal, but we need a particular assumption. This distance must be, this distance estimate must always be less than or equal to the true distance. So a heuristic which always underestimates the distance is called an admissible heuristic. And so as long as this is always an underestimate, we can prove that this finds the shortest path. Okay, and in the case of this distance, it's obviously the straight line distance is going to be an underestimate of the road distance. Okay, now how do we prove that it'll find the shortest path? Well, again, this is the start node, and we always have this inner ring of nodes that have been expanded, and then we have an outer ring of nodes that have been generated. Now, when we decide to expand this node n based on this part of the path from S to n, and then this dotted line is our estimate of the distance from n to g. which is always less than or equal to the actual distance, which is shown like this. So that's h of n, and this distance along here is h star of n. Now, if we get to the point, at what point does the algorithm stop? Well, it stops at the point where we're going to expand the goal state, not generate it, but expand it. So the algorithm has considered all of these nodes and calculated this function, and this node here is the one that has the minimum, and that's the one it's expanded, okay? Now, I'm sorry about the little g and the big G, but this term here is the actual path from S to G. This here is meant to be the heuristic function of G, but this is the estimate of the distance to G. So if this is the true distance from G to G is 0, and h of g has to be less than that, so h of g must be equal to 0. So f of g must be equal to just the actual path length. Now, to prove that this is the shortest path, well, let's suppose that there's some other path that's shorter. So let's suppose there's another path from S to G which is shorter than this one, and then we're going to get a proof by contradiction. So we don't know if that path could go to the same goal or it could go to a different goal. We don't know. It doesn't really matter whether it's the same goal or a different one. Let's assume it's a different one just to keep the picture simpler. So here's another path that goes to a goal. So now that path, in the beginning it stays inside this circle of expanded nodes, but then there's some node here where it's the first time it comes outside of this circle. So there's got to be some node n along this path which has been expanded, which has been generated but hasn't yet been expanded. And so then you've got to ask yourself, well, why is it that this node got chosen for expansion and not that one? Well, it must be because f of this node is bigger than f of that node. So f of g is less than or equal to f of n, but we just said that f of big G is equal to the actual path length. F of n is equal to g of n plus h of n. H of n is a underestimate of the true path length, so this must be less than or equal to the true path length. And that tells us that this path must be longer than that path. Okay, if you go through the video and repeat it if necessary, I think you'll see the logic of this better. But this basically proves that the A-star search will always find the shortest path. And this is from the textbook. This gives the same argument but in a slightly different way. Okay, so these are the properties of A-star search. It is complete, provided there are not infinitely many nodes whose cost is less than the solution, which is true in all the cases we're interested in. It is optimal. The time and space are still exponential because it still has to keep all nodes in memory. Okay, so are there any questions about this A-star search? Yes? The A-star search. Good question. I think that this I think it dates back to 1967. So I mentioned about that missionaries and cannibals problem, that Amarell paper. I have to check. I think it may have first been introduced in that paper or around that time. Yeah, around about the late 60s, early 70s. And what's it being used for? Well, a lot of things. Good question. So I'm going to talk a little bit about Rubik's Cube. It's certainly being used to solve, find the quickest solutions to Rubik's Cube. Now you could say, okay, this is just like fun and games, but it's also used for path planning and a good example, Google Maps. Yeah, so how would, since you raised the issue, how would you, well, you can think about how, in this case, we're minimizing the distance. So, well, let's think about train scheduling first. So if you were trying to find a way to get from one city to another by different trains, you would have to take into account not the distance, but actually the time for the train to make the journey, and you'd have to make sure that you get off the train, that this train arrives before that train leaves, and so on. But you get the same kind of algorithm with just a few enhancements. Now with Google Maps, that's interesting too, right? You want to minimize not the distance, but actually the time. So it tries to keep, and Waze.com does the same thing. It tries to keep track of how congested the road is. So whether it's going to take longer to do this road or that road. And it tries to have that information in real time if you're doing a search for, you want to do it now. But if I say, well, I want to drive this thing tomorrow morning at 9 o'clock, it'll make its best guess at what the traffic's going to be like at 9 o'clock. So, that's actually a really good example of a practical application. And if at some point, I'm not sure if it's next week or after, but I'll give you an example also of like robot path planning. Yeah, good question. Okay. So then the next question is, how do we come up with admissible heuristics for some of these other domains? So if we look at the 8 puzzle, how would we, so let's think about the 8 puzzle. So if we wanted to do breadth first search, again, it would take too long because it's expanding out in all directions. We want to use some sort of heuristic. So how would you come up with a heuristic for the 8 puzzle? So what we want to do is you're given a state and you want an estimate of how many moves it's going to take you to get to the goal state, and it has to be an underestimate. So how do you, well, okay, so one approach is to say, one approach may be just to say, well, how many notes, often it comes from what's called a relaxed version of the problem. So, something funny has happened here, okay. So I could say the number of misplaced tiles. So this is saying, okay, well, node 6, this tile is already in its where it should be. So I don't know whether that's going to have to move at all. But tile 4 is not where it should be, so tile 4 is going to have to move at least once. And tile 7 is also going to have to move at least once. So there's 6 tiles, only one tile can move in each step, and there are 6 tiles that are out of place, so it's going to take me at least 6 moves to solve that puzzle, okay? Now, that is an answer, but the trick here is it's called like brinkmanship. You want to get an estimate that's as close as possible to the true distance without exceeding the true distance. You want to get as close to the cliff as you can without falling over the edge. So 6 is an underestimate, but it's a very, very serious underestimate. It's much, much less than the true value. It's more intelligent to say, okay, 4, the 4 is actually here but needs to be over there. What's the minimum number of moves that the 4 tile could make in order to get to its correct position? Three, that's right. At some point, you know, the 4, we don't know other tiles are going to move in between, but the 4 has to get somehow from here to here. It could go like this, 1, 2, 3. It could go 1, 2, 3, or it could go 1, 2, 3. But somehow the 4 has to move at least 3 times in the course of solving. It may be even more, but at least 3, right? And the 1 has to move at least 1, 2, 3, 4 times. So this is called the Manhattan distance. So the Manhattan distance from here to here is 3, and the Manhattan distance from here to here is 4. This is because in Manhattan all the streets are like on a rectangular grid. So this is like the distance you would have to travel in Manhattan. You'd have to walk in Manhattan to get from one street corner to another. So if you figure all this out, the 1 has to move at least 4 times. The 2 is in its correct position. The 3 has to move at least 3 times. So if you calculate for all of these tiles, you can deduce that at least 14 moves must be required in order to solve the puzzle. So here's 2 different heuristics. That's the missed player's tiles heuristic. This is the distance from goal position heuristic. And each of these can be seen as a kind of relaxed version of the problem. So if you took the problem and relaxed some of the constraints, this is how many moves it would take you. So the Manhattan distance is saying, well, let's assume that you're allowed to slide one tile over the top of another tile. You're not normally allowed to do that, but let's pretend we are allowed to do it. Well, then it would take me 14 moves to solve the puzzle because I could just kind of slide these things over the top of each other. And this is getting even more relaxed. It's saying, well, let's imagine I could just pick up a tile and move it anywhere I want in one move. Then it would take me 6 moves. Okay. Now these this heuristic is said to dominate. Sorry, this heuristic is said to dominate that heuristic. For any state, this heuristic is bigger than that one. And in general terms, if one heuristic dominates another, then the one that dominates is better. Now, this is some examples. So we got the 8 puzzle, and then we got the 14 puzzle, and then we got the 24 puzzle. So the 8 puzzle is 9 by 9. It's 3 by 3, giving you 9 squares, but one of them's blank, so that's why it's the 8 puzzle. The 14 puzzle is like 3 by 5, and the 24 puzzle is 5 by 5. So you can do some computer simulations, and the code that I've provided can do this as well. How many nodes are going to be expanded when you solve the puzzle? First of all, just using iterative deepening search, so not using the heuristic at all. Then using A-star search with the weak heuristic, and then doing it with the stronger heuristic. And you find that the number of nodes expanded decreases massively. So the 14 puzzle with iterative deepening search, it expands 3 million nodes. A-star search even just using the weak heuristic, only expands 500 nodes, right? So this idea of guiding the search towards the solution saves you an enormous amount of search, and with the 24 puzzle it becomes bigger. Iterative deepening search takes 54 billion, expands 54 billion nodes. This reduces it to 39,000 and this to 1,600, right? And probably for the second assignment, you probably will be taking that Prolog code and running some of these. You won't have to write code, but just run the code and measure how many, keep a record of how many nodes get expanded. Any questions about this? Okay, so the final segment for today is about how to find admissible heuristics, and we're going to use Rubik's Cube as an example because it's a very good, very illustrative example. So as I mentioned, these heuristics often come from as an exact solution to a relaxed form of the puzzle, right? Now, here's another thing to notice. Let's suppose I find several heuristics. Let's say I find two heuristics which are both admissible. If I compute the maximum of those two functions, that's also going to be admissible. Because if h1 is less than or equal to the true value and h2 is also less than or equal to the true value, then the maximum of h1 and h2 will be less than or equal to the true value. So if we may find one heuristic which is a good estimate in some cases but not others, and vice versa. If we combine two of those heuristics, we may get one that's generally good. Okay, so now let's think about this for a minute. How would you define, how would you come up with a good heuristic for this Rubik's Cube? Now, so what we're doing is, I give you the cube in a particular state, and you have to estimate how many moves it is away from the final from the goal state. Now, the first thing you might think of is, can I do a three-dimensional version of the Manhattan distance? Right? So, well, okay, let's back up a little bit about this. So, when you first see this puzzle, you think about it in terms of like little stickers, right? But then after a while, you realize, well, it's actually more. It's better to think about it in terms of little cubies, right? So you've got little edge cubes and little corner cubes. I think I told this story on the video. You know, this puzzle. When I was in high school, this puzzle was a real craze, you know, and everyone was doing it on their way to school and at school. And yeah, a friend of mine who used to catch the bus to school, he overheard two girls sitting behind him talking about Rubik's Cube. And they were at the stage where they were just trying to get one side, you know, not the whole cube, but just one side. And one of them is saying like, oh, you know, I can't get this side, you know. And the other one said to her, well, you know, I think that's because someone told me that blue is the hardest side to get. You should try getting the green side, you know, that's much easier. So, okay, so how many edge cubes are there and how many corner cubes are there? Sorry? How many corner cubes are there? How many corners are there? 8, right. So there's 8 of these little corner cubes that have 3 little faces. And how many edges are there? 8 edges. How many edges in a cube? 12, right. So there's 12 edge cubes and 8 corner cubes. We don't worry about these middle cubes because these middle faces, these middle ones just spin around and don't do anything. Okay. Now, so if we were trying to come up with a three-dimensional version of the Manhattan distance, you might say, well, if this cube is here and it should be there, then I need at least 1, 2, 3 moves to get it from here to here, right? But the problem with this is, unlike in the 8 puzzle, only one piece moves at once. Here, 4 corner cubes move at once, right? So I would have to add up the Manhattan distance and maybe divide by 4 or something. I do get a heuristic, but it's a very, very weak heuristic, right? So this constraint satisfaction guy called Core first looked at this in the 1990s, and he said, okay, right, so the 3D Manhattan distance, if you include edges and corners, you'd have to divide by 8 because 8 of them move at once, right? So if you just did it for the edges and divided by 4, that gives you a slightly better result. So I don't worry about the corners, I just worry about the edges. I know all the edges have to be in the right place. So I figure out, for each edge, I figure out what's the minimum number of moves required to get that edge into the right place. And I add that up, but then I have to divide by 4 because 4 of them move at once. And you could do the same for the corners, but it turns out the corners doesn't give you much extra benefit. Okay, so what's a better approach? Well, he said, okay, let's suppose we forget about the edges altogether and we just look at the corners. Now, if you just want to solve the puzzle with regard to the corners, it's a much simpler puzzle. It's like solving a 2 by 2 by 2 cube. And in fact, the whole problem could easily be solved even with the computers of the 1990s. I think the total number of states is about 3 million. So he said, okay, I'll take the corners and if you give me a cube, I can look at the position and orientation of all the corners, and I can tell you exactly how many moves it would take to put all the corners into the right place. I can pre-compute this. I do this pre-computation for all of those 3 million states. I figure out exactly how many moves it would take to get the corners into the right place. Yeah? And so this is a classic example of a relaxed problem. I'm relaxing the problem by saying, well, I don't have to solve the edges, I just have to solve the corners. And it's possible to solve that exactly by just doing I create a database of all the positions and I do a full search, and that'll tell me the size of the quickest solution for each of those. So then you say, okay, that gives me a heuristic for the original problem. If I know that it's going to take exactly 11 moves to solve all the corners, obviously it'll take at least 11 moves to solve the whole puzzle, right? So that's very clever. And then you say, well, what about the edges? Can you do the same for the edges? Well, it turns out that the edges, there's 12 edges, and the number of combinations for all 12 edges is quite large. It's kind of really too large to search the whole thing completely. So he actually arbitrarily divides the edges into 2. He picks, for the solved cube, he picks, the 6 edges on this side and the 6 edges on that side, and he treats them as 2 different sets. So he's, okay, what's the minimum number of moves that would be required to solve for these 6 edges? He pre-computes that. what is it for these 6 edges, he pre-computes that. So that gives him 3 heuristics. 1 heuristic based on the corners, 1 heuristic based on 6 edges, and 1 heuristic based on the other 6 edges. So he's got H1, H2, and H3, and then he takes the maximum of those 3 heuristics. And this is very clever because if you think about it, there'd be some situations where there's some situations where the corners are nearly right, but the edges are very wrong, and there's some situations where it's the other way. And so by taking the maximum of these 3 heuristics, he gets a sort of generally good heuristic, that covers different cases. And so by doing this, he was able for the first time to use A-star search to find like minimal path length solutions for Rubik's Cube. And of course, this has gone, if you look, people later have used this to build robots that will solve it. It got down to 20 seconds and then 10 seconds and 3 seconds. And I think there's a robot now that claims to be able to solve it in 1 second. Okay. So just a couple more, just a couple more details about this. Someone was asking at the break whether there's a equivalent of iterative deepening search for other searches. So the answer to that is that there is something called iterative deepening uniform cost search, and there's iterative deepening A-star search, and actually Korf actually used iterative deepening A-star search for this because it's still, even with his really good heuristic, using A-star search still ran out of memory. So the way iterative deepening A-star search works is you fix a certain value of f of n plus g of n, and you do an A-star search, but you cut off the tree whenever it exceeds that predetermined value. Then you increase it, and you repeat the process, and you do it again. Okay, so IDA star search actually can solve this problem where A star search fails because it uses less memory. And I've got Prolog code there that does IDA star search as well. Okay, so I'll just tell you we've managed to cover up more or less up to module 4 now. If you want to have a look at this, as I mentioned, this maze widget, there's 2 versions of the maze widget. So if you look at the one in the informed search, it gives you more options. So you can choose iterative deepening search and A star search and so on. So you can have a play with this. If not this week, try to do it next week. Any final questions? Yeah. Good. Okay, so I'll see you next week.
I'm very confused because I don't actually know how to use them.
Right.
So what I'm expected or what I'm supposed to learn from today's lecture is like there are all these prices, pros and cons for how actually
Yeah, I mean, you should have a look at the videos, especially these little short videos. So there's longer videos and then there's little short videos. Try to have a look at those, and then try to play around with this maze widget to get a feeling of the benefits of the different algorithms.
And what am I supposed to memorize or to learn? Just the iterations.
Well, you should. Okay, I think, for example, well, have a look at the tutorial questions. So for this week, it's mainly for this week it's mainly about uninformed search, but there's a little note that says you can do a couple of the next week's modules as well. And then when you get to next week, look at those tutorial questions. So, and also there's these little activities you should be working through as well. So like every, let's see, like breadth first search. Yeah, there's probably the breadth first search, and then there's little exercises. So you try to drag over. You try to type the answers in here and then check your answers. And
but still, it's even if I can't finish all these quizzes, but it's I still can't really use all those methods.
Can't implement them, or can't?
Yeah, I just can't implement them. I guess.
Just
so it's I'm not required to implement them, just to know them.
That's right.
Yeah. And it's in which form will they be delivered in the exam or something?
If you work, if you go through the tutorial questions, they give a kind of pretty good indication of the kind of questions in the exam.
So basically, it's just go to the tutorial and answer all the questions and help you.
That's right, but try to have a go at answering them before your tutorial if you can.
All right, thank you so much.
So, is all the extension material course outline, or is there some stuff missing from the 9.818?
We've some of it. It's I think from last year when we had the. So some of it we. Okay, a couple of topics.
Yep.
We're going to probably cut.
Okay.
But others we will cover, but a little bit late. So I will do the reactive agents, for example, and the evolutionary robotics.
Cool.
But I'm just kind of waiting for an appropriate time to slot them.
No, I just saw that there's some references to bits that aren't there anymore in some bits. Okay, cool.
Yeah, I'm trying to kind of juggle it.
Do you know from memory how full the tutorial at 5 p.m. on Mondays and Wednesdays are? Not too sure. Okay. I might just have crap.
I'm sure that there's space.
Okay, awesome. Thanks.
Yeah. Yes.
I saw some courses in your slides, but it's relevant to this class.
Yeah.
I want to let me some suggestions about some courses that can be related to for next step.
Yes.
More relevant about CNN, about artificial image processing and AI